Welcome back friends. So we have been looking at Green's functions method to calculate simple process in QED. QED is a theory with one photon and one electron, and we started drawing some simple process in which in this particular fashion, okay, where I wrote the photon as a dynamical field. Essentially the photon as a dynamical particle, essentially it just goes as okay dynamical particle, and it is a virtual particle essentially. Now in the entire process I did not tell you that now these calculations can be done even if the photon like I have been mentioning that these calculations with the interactions can be the same Green's functions methods can also be applied when the photon is also not quantized essentially. But let us okay, when the photon is also not quantized, but the Dyson equations show you that you can have the photon field also dynamical essentially. And then when we listed out the QED process, simple process, we started with a process in which the QED itself, and when we wrote down the Feynman rules and everything, okay, we wrote down not just the propagator, but we also wrote down the Feynman rules from the Dyson equation. We also wrote down the process in which the photon could be dynamical because it comes as an external particle essentially, it comes as an external particle in the interactions essentially. So when we want to write it in terms of external particle, it is better to write it as a dynamical field, it is quantized. And so what I did in the previous lecture before, when I assume that the photon is quantized essentially and it is treated as a particle with a particular moment epsilon and a polarization vector, okay, and then I showed these two diagrams contribute to the process essentially. And after that what I did was I took a detour and showed that the photon field solutions can be actually be quantized, but I did not go into the full details of the second quantization because I believe that that would require a quantum field theory, okay, which we will do in the next semester or something essentially, okay. But independent of that, we can always say that the solutions can be written in this particular fashion. You can start with del A mu is equal to epsilon mu k e power I kx, and then write down the solutions for this, and then you can use the procedure of canonical quantization. What I wrote down, these steps 1, 2, 3, 4 are the steps for canonical quantization. These are the steps for called canonical quantization. Okay, this involves writing down commutation relations essentially for at equal time, essentially for equal time. So okay, equal time commutation relations, okay, and then in field theory language, which okay, but the crucial point is that we can, without going into the details, but I tried to follow the philosophy of Sakurai here essentially to give you a flavor of the thing, saying that I can express this in terms of this directly express these things in terms of raising and lowering operators or creation and annihilation operators, which are A and A dagger given for each mode essentially, which is for each mode of k and each polarization vector epsilon essentially. The polarization vector has two values epsilon 1 and epsilon 2 because the photon only has two polarizations, and k can have infinite values essentially, it can have infinite values. Because the k has infinite values, you will have infinite number of A dagger and A operators. So if you write the spectrum from the Hamiltonian, essentially you see that the 0 point energy of this of the simple harmonic oscillators will end up being infinite essentially. The vacuum the lowest energy state is a vacuum state which has infinite energy. So the infinite energy should be rescaled away, which should be removed away essentially, and which we can do because what we measure exactly like in Dirac-C, which also has infinite energy. So what we can do, what we measure is only the differences in the energy values of the states, and so we define this essentially. Okay. This entire treatment makes a photon like is a dynamical particle. Now with this detour we go back to the Compton scattering essentially. So the Compton scattering, the QD the Compton scattering is given by this. So Compton scattering is electron photon scattering. It has two channel diagrams essentially, one is S channel diagram and another is a T channel diagram. Now remember there is what you call S and T and U are essentially they are not independent, but you have to give them same labels essentially. So what is typically called as S and T are the ones which I am using essentially. The photon wave function is just the wave polarization vector as I have mentioned here. Now the Feynman rules here for this QED, I think I have spent some time on them as an here it is. The Feynman rules are essentially the vertex has a coefficient E I gamma mu. The incoming electron has U wave function, the outgoing electron has U bar wave function, the antiparticle is V bar and the particle is outgoing is V. With this what I did was that I could calculate for the one of the diagrams essentially of this process. I wrote the amplitude in this particular fashion essentially. What we are calculating here is the amplitude, and then if you want to calculate the differential cross section you have to take the square of the amplitude, which is nothing m dagger essentially. Okay. I did not do the steps essentially. If you have m dagger I directly wrote down the scattering cross section in the lower origin limit when p goes to 0 essentially as this particular fashion. There are certain theorems essentially which helps you. So when you are doing the computation there are certain theorems which are very useful essentially, because what is happening here is you remember that the Dirac equation is a matrix and the solutions are all unit or column vectors, essentially U and is a column vector. And U bar is a row vector. So what, and then you also have, if we have Dirac propagator in between, Dirac propagator is a matrix. So Dirac propagator is a matrix. With this, so you have to make sure that what you are writing down at the end of the day should be a number. You are dealing with columns of vectors, matrices and so on. Gamma matrices are also there, which are also the problem. So when you do this, what will happen is the matrix element, if you have one single diagram, the mod square is nothing but m dagger m. This is will be ended up be equivalent to computing traces of the matrix element. So the amplitude square is nothing but most of the time is computing the traces of the matrix element essentially. So what you are computing is the traces of the matrix. So when you are computing the traces of this matrix element you have to use several properties essentially. So some of these are very useful properties which I will list a little bit of few of them here essentially. So one of this so let me list a few of the trace formula essentially. The trace number of odd number of gamma matrices is 0. I list a few theorems, I will not prove, okay. Some of them will appear as assignments to you essentially. or also called, okay, let me call them as what is well known. So one of the first theorems is the trace odd number of gamma matrices is 0. Now this is all relevant only to Dirac theory essentially, because we are only dealing with the Dirac theory. Okay. So what we have is essentially that if you have some momenta or some A slash, or A is some vector essentially. So trace A1 slash A2 slash AN slash is equal to 0 when n is odd. Okay, when n is odd. So this, now you have the formula that gamma phi, since gamma phi square is equal to 1, you can also modify this trace A1 slash A2 slash AN slash gamma phi is equal to 0. This is equal to trace gamma phi A1 slash AN slash gamma phi is equal to 0. Okay. This is one of the first trace theorems essentially, which is very popular and very important essentially. The second trace theorem, I am not proving this thing. Okay, most of the proofs are left for proof is left as exercise. These the proofs are very simple. All the starting point of any of the trace theorems proof is essentially the commutator between gamma mu and gamma nu. The anti-commutator of gamma nu is 2 times eta mu nu. You start with that, take the trace of it, and that gives you 4 and so on. So you can start with that and take the odd number and then use the anti-commutators between them, and you see that odd number. If you take 3 gamma matrices immediately, the trace of that, it just goes to 0. You can show it immediately because the anti-commute essentially get a minus sign plus sign, and then you get a contradiction like minus sign is equal to plus sign, and that is only true when for the same quantity. So minus sign is equal to plus that quantity, and that means this is only possible when that quantity is 0. So most of the trace theorems have always come up to this contradiction. So I welcome you to practice these things essentially, and then play around with these things essentially. The second trace theorem is equal to trace 1 is equal to 4, and trace A slash B slash is equal to A dot B. Okay, there is a 4 essentially, 4 A dot B. So trace of unity matrix is 4. This is obvious essentially because it has 4 diagonal entries, and trace of A slash B slash A slash. So let's imagine that A slash is P1 and P2, B is P. So if there are 2 momenta essentially P1 P slash and P2 slash, trace of P1 slash P2 slash is equal to 4 P1 dot P2. Okay, it's 4 P1 dot P2 essentially. Okay, and then there is this cyclic property of trace theorems essentially, which I leave it to you essentially. Okay, so this will be like so if you have a trace of A1 slash A0 slash, so let me write it down essentially. Cyclic property. I thought I'll skip it, but anyway I'll just use it. So trace A1 slash A2 slash AN slash is equal to A1 dot A2 trace A3 slash A4 slash AN minus Okay. So then you take one of the AIs essentially minus so and so plus 2 AI dot an trace it 2 slash an minus 1 slash minus trace a2 slash an slash a1 slash. So you can always go around with the trace, essentially put back a1's, you can take the a1 on the right essentially like here what I did essentially. So you can keep moving 2 at a time, and this becomes useful when you have very complicated traces. And nowadays most of the trace formulas are evaluated on a computer, okay, evaluated computer using programs based on Mathematica called FineCalc or based on symbolic manipulation called FORM. Okay. So either you are using FineCalc or FORM essentially, and you calculate these things automatically. You don't really early in, but it is good to know once in a while to check whether what you are calculating makes sense or not essentially. Okay. So it is always good to know these things, and then there are these nice other theorems. Trace of gamma phi is equal to 0, gamma phi a slash b slash is equal to 0, trace of gamma phi a slash b slash c slash d slash is equal to 4 I epsilon alpha beta gamma delta a alpha b beta c gamma d delta sigma essentially. Okay, and epsilon alpha beta gamma sigma is plus 1 for even permutations of 0, 1, 2, 3 and is equal to 0 for odd permutations. Okay, I will then list one more theorem essentially. Then there are many other trace theorems essentially which we can go. Okay, there is also theorems on other things essentially. I will just list one more of these things. Theorem 5, this tells you that gamma mu is equal to 4. And now this is very simple to prove, that it is just eta mu if you put in or g mu if you put in, you can show that this is always true essentially. Now gamma mu d slash gamma mu, this will appear minus 2d. So let me call it a slash minus 2 a slash gamma mu a slash b slash gamma mu equal to 4ab gamma mu a slash b slash c slash gamma mu is equal to 2 c slash b slash a slash, okay, and so on. So you have these nice theorems essentially which you can use, and these are all relevant to calculate. And if you have, so if you have odd number of gamma, if you have even number you have this, if you have odd number you can express it in terms of products and everything essentially. So if you have only 2 or something you can express them in terms of dot products. If you have 4 of those essentially it becomes you can take 2 things at a time and everything, and you can you have some gamma mu, say a slash b slash c slash d slash gamma mu. So this is equivalent to 2 times d slash a slash, and then you have b slash c slash plus c slash b slash a slash d slash. Now I do not want you to memorize all these theorems essentially, but these are all useful theorems which can be useful, but it is better nowadays, but it is better to calculate and check these theorems once in a while essentially, okay. Okay, and last theorem I will mention, trace a slash a2 slash, if you have n number of even number of p1 slash p2 slash and everything, this is equivalent to a2 slash a2 minus 1 slash a1 slash. Okay. With this these are the 4 basic theorems which you can use essentially, and I think I said 6 theorems, but most of them are derivative essentially. You start with one. This I think this requires to prove charge conjugation. This requires to prove charge conjugation, but otherwise most of the things can be proved just by the properties of the gamma matrix, simple one of the properties of the gamma matrices. Okay, so what we have seen is that now you start with this so going back to the Coulomb scattering, so you do this or Coulomb or Compton scattering essentially, not Coulomb scattering. So you take this S channel and T channel diagrams, express this entire thing into these 2 amplitudes. You have one amplitude in this particular fashion. Similar amplitude you can write down for this thing essentially, okay, for the T channel diagram, which is nothing but given in terms of P4 minus P1, and for the propagator this is the Q. For the propagator assign momentum properly essentially, assign momenta, and Q is equal to here P4 minus P1 square, Q is equal to P1 plus P2 square. Okay. Now with this now you can write the amplitudes. After writing the amplitudes, in this particular fashion can write down these amplitudes for M1. Similarly for M2 the difference is nothing but you can express this, you have the same thing U of P bar and U3 of U, U3 of P, and only the propagator becomes different, and with different energy essentially, and the momentas of the photons are different. Otherwise the amplitude will look exactly the same. It has the same Lorentz structure, the amplitude has the same Lorentz structure as M1, okay, except this propagator amplitude is different essentially, except this propagator. This is the momentum mass of the electron essentially, okay. In this case now you can, with this and using the completeness of the photon wave functions essentially, photon wave functions and UU bar and this thing, you can write using the trace theorems. So now you can have M1 plus M2, okay. So here so when you do M1 plus M2, okay, now if you want to calculate mod M square, this gives me M1 square plus mod M2 square plus M1 star M2 plus M2 star M1, okay. These are called interference terms. So these tells you that both the diagrams have cross terms between them. Essentially these are the diagrams which are cross terms between them. So these diagrams are called interference terms, and they can play a very important role in certain cases. Essentially the interference terms play a big role essentially. So the two diagrams don't just add up, the two diagrams, because we are in but one should not forget the interference terms, okay. One should not forget these interference terms, and using these interference terms you can calculate, and then using the trace theorems, okay, trace theorems, you get these particular solutions. Essentially you get the cross sections in this particular fashion, and then this is the cross sections. To achieve this you need to use the trace theorems. So what we have seen is that using the trace theorems everything, okay, there is a very nice interesting limit that in the low energy limit P goes to 0, essentially the Thomson scattering happens essentially. Okay, good. With this we have seen the first example. In the next examples let us try to draw the Feynman diagram for Baba scattering, molar scattering, pair annihilation, pair creation. In all this process let me right now treat when I am drawing these diagrams the photon as a dynamical field. I will come back to Coulomb scattering because I want to connect it to the case when we need it, say for example correcting say with the final chapter of this thing would be calculating relativistic corrections for the hydrogen atom. That is the basic idea essentially at the final thing, okay. So before that I want you to do this simple things like where I will treat in the dynamical sense, then we will come to the non-dynamical calculations essentially, okay. So let us do the other examples. So we have dealt with Compton scattering. So let us look at Baba scattering. Now Baba scattering we have seen the pion example. It's the same thing here also. So we have seen this pion example. These are the two diagrams, the T channel diagram and the annihilation diagram. So it is exactly the same thing. Okay. The annihilation diagram. So electron comes, okay, anti-electron comes, photon, electron goes, anti-electron goes. So there is a nice charge conservation here. Okay. So this we call it a P1, P2, P3, P4. See the momenta, this is Q, this is a S channel process. Annihilation diagram. And then there is the T channel process in which the photon goes, time is in this direction. The positron keeps, the positron goes like this, the electron goes like this, and the positron goes like this. Electron, they exchange of momenta Q. So P1, no P1, P2, P3, P4, Q is equal to P2 minus P1 square essentially. So this is the T channel process. This is called the scattering part. So the positron and electron need not just annihilate all the time when they see each other, they can also scatter, and that makes a difference essentially when the annihilation channel becomes important, because when the energy exchange is greater than 2m square, the annihilation channel becomes important, and before that the scattering channel is the most important thing essentially. Okay. When with the annihilation channel becomes important when the energy of the scattering is greater than twice the mass of the electron essentially, twice of the mass of the electron. Good. Okay. So we have seen the process of the Baba scattering. Okay, and I'll stop here, and then we will do this simple. Now this can be calculated in the same fashion essentially. Okay, using the amplitude technique which we have seen, writing down the Feynman rules and explicitly writing down the Feynman rules, computing the amplitudes, using the trace theorems and so on. So, and finally you get an answer, essentially the Baba scattering answer. Now you can do the same thing for the molar scattering, also and so on. So we will do these things in the next class essentially. So let me stop here, and we will continue in the next class. Thank you very much. Okay.